So let's suppose that we're interested in a first derivative of a function. Now we're making the assumption that we have the function to work with, meaning that we can plug any value of x and we can get the value of the function at that point x. What we don't have is we don't have any means of computing the first derivative, so we don't have some analytic solution for how to differentiate the function. Instead, we want to estimate the first derivative. So the definition of differentiation, if we remind ourselves of what this is, the definition is that df by dx is actually a limit with some delta x going to 0, of f of x plus delta x minus f of x divided by this delta x. So that's our formal definition. Now we can actually try using this formula to get different approximations of first derivatives. And there are actually different approaches to how we can go about it. So the first approach that we're going to take is called the forward difference. So the forward difference approximation is actually defined as follows. So we take df by dx at some point x being equal to xi, and we define it as the following. We say that we're going to take the function at xi plus 1, kind of the next point, subtract the current point fxi, and then divide everything by xi plus 1 minus xi. So what does this mean? Well, let's actually try drawing it. Let's draw just a very simple graph here. So this is the actual graph that we maybe want to find the derivative for. This is the actual point x for which we're trying to find the derivative. I'll call it xi, assuming that there are points to the either side. So xi is what we're interested in. Specifically, we're interested in the tangent, the slope, which might be something like this. So we're interested in this slope. However, since we don't have an analytic solution, we're not going to quite get this slope. Instead, what we're looking at is we're looking at other points. We're looking at xi minus 1 and xi plus 1. So we can sort of position them here, for example. And in the forward difference, we only interested in xi plus 1. So here is some other point xi plus 1, and this point also happens to have a corresponding y value, obviously. So then what we're saying is that if this line is the true derivative of the point, the function at xi, then the approximate derivative is taken as follows. So we're essentially drawing a line from this point to this point, and we're saying that this is our approximation. So essentially what I can do here is I can draw this line. Well, it's not a very straight line, but you hopefully get the idea. So this line is our approximate first derivative. As you can see, the slopes are completely different. So it might not be the greatest of examples for this particular function because it's so curved. Now there is a point xi minus 1 here that we don't need for the forward difference, but we are going to need it for the backward difference. So the backward difference is actually very similar. So let's have backward difference. Okay, so the backward difference, I'm just going to go back into this function. So the backward difference actually takes the point at xi minus 1. So essentially the definition is very similar to what we had before. So df, let's do it like this. So df by dx calculated at x equals xi is actually taken as the following. Now here we took the current point and some point next to it, And we can do the reverse. So we can say that we're going to take the current point, fxi, we're going to subtract the previous point, f at xi minus 1, and we're going to divide once again by the difference in the x value. So that's xi minus xi minus 1. So essentially, we're now saying that we're going to consider this particular point, this point here, and we're going to look at the slope, which goes like this. So it goes through these 2 points, like so. Okay, let me actually let me do the labels a bit better. So I'm going to wipe out this part, and instead let's have so this is the forward difference approximation, and this line is the backward difference approximation. Okay, so this is the two options, but there is another option, and the other option is called central difference. Central difference. So the central difference basically takes the previous point and the next point. So essentially its definition, I'm sure you've guessed it already, but let me just spell it out anyway. So df by dx at point x equals xi is estimated to be the slope between this point and this point. So in terms of our definition, that's fxi plus 1 minus f of xi minus 1, all divided by xi plus 1 minus xi minus 1. So once again, what we do, let me actually pick a different color here. Just a moment. I'm going to pick a different color, and we're going to draw yet another line, which is perhaps the best line of them all. So we're going to have a line that goes something like this. So this line is the central difference. And as you can see, it's pretty close in terms of slope to the true line. So here is the true line, and the central difference is getting pretty close. Now let's actually look at an example where we calculate these differences for a set of particular values, set of particular functions, and let's actually see what we get when we plug those in. So we're going to assume that we have the following function. So we're going to have a function f of x being equal to 3x squared. Okay, and we want to evaluate f prime of x at a point x equals 2. So we want to calculate the first derivative at x equals 2. So we do know analytically that the first derivative of the function is actually 6x. So the value of derivative at x is equal to 2 is actually equal to 12. But we're going to ignore that for now, because we're essentially going to do numeric differentiation as opposed to analytic differentiation. So first of all, we need the values of f of x. So we're going to since we're calculating it at x equals 2, I'm going to take the values of x of 1, 2, and 3 for our backward difference and forward difference and central difference approximations, and then I'm going to calculate the function f of x for all of them. So it's going to be our little table of values. So f of 1 is equal to 3, f of 2 is equal to 12, f of 3 is equal to 27. Okay, so now we can calculate those finite difference approximations. So first of all, let's do the forward difference. So with the forward difference, we're essentially calculating f of 3 minus f of 2 divided by 3 minus 2, and that's equal to 15. So that's not quite the same as 12. In fact, if we calculate the error, so the error is actually equal to 15 minus 12 divided by 12. So that's 3 over 12. So that's essentially 25%. So we got a 25% error. Now let's do the backwards difference. So second option is backwards difference. Once again, we do f of 2 minus f of 1 divided by 2 minus 1, and that's equal to 12 minus 3 divided by 1, which is equal to 9. So 9, once again, is not the same as 12. And if we calculate the error, we get 9 minus 12 divided by 12 modulus. So that's once again a 25% error. So in both the finding difference and the backward difference, we're actually getting quite a significant error. Obviously, if we moved the points, if we move the points 1 and 3 closer to the value of 2, we might get better results. But for this example, we're not going to do that. We're going to consider the central difference next. So finally, let's do the central difference. So the central difference is where we take the 1 and the 3. We take the edge values. So we get f of 3 minus f of 1 divided by 3 minus 1. So that's 27 minus 3 divided by 2. And that's 24 divided by 2, which is 12. And our error is equal to 0 because that happens to be the correct result. So once again, the results show that the central difference actually gives us a more accurate estimate.